Thank you for the invitation. I'm Kenneth Lance Gould. I'm Professor of Medicine and Cardiology and the Distinguished Bucksbaum University Professor. I've been here since 1979, and so the question is, why did I come and why did I stay 40 years later? And it's a marvelous question because it's a unique place. So I came to pursue a passion in coronary physiology, how the heart works, the blood flow, that I had developed over my time in Seattle for the prior 10 years, and came here to convert that into clinical application. So in order to kind of explain why and what was the historical setting, when I finished cardiology fellowship in Seattle, the angiogram had just been introduced, the coronary angiogram. Bypass surgery had just been started. It wasn't widespread, but started. And there was the initial first myocardial perfusion imaging blood flow in the heart with very crude instruments. So these were the three factors that in my 10 years in Seattle kind of blossomed to dominate all cardiology. But in my view at the time, I was interested in physiology, and what I realized was that no one had ever understood or measured quantitative blood flow, how the stenosis worked. So I started a series of experiments that made me quite famous in terms of defining stenosis with the pressure flow equations and experimental models. Also the concept of coronary flow reserve, capacity for flow to increase. Both these concepts became worldwide very quickly, and then realized that I had to have another test besides exercise test. I trained with Dr. Bruce for the Bruce treadmill test over these 10 years, and it's hard to exercise people seriously and in series in order to study a series of experimental stenosis. So I looked into a drug and invented the concept of pharmacologic stress. You give a pharmacologic agent, you increase the blood flow, and you take a picture of the blood flow at stress compared to rest, and you can see that the flow is restricted by the stenosis. All that came out of my lab. I published a lot of papers and had kind of finished the concepts experimentally. So I was a well-known coronary physiologist, but also cardiologist. So that was the background in Seattle. What was happening in Houston? During those times, Mike DeBakey had developed the bypass surgery, and the surgery here, we're doing 30 to 40 pumps a day. So Houston was the bypass capital of the world. And Denton Cooley and Mike DeBakey were the leaders. And it was good medicine, good surgery, but the science wasn't heavy duty. So where was UT? They had just lost all their cardiologists left and went to Park Plaza. There was a new chairman of medicine, and he wanted to start a scientific cardiovascular program, so he offered me to be chief. So I said, oh, great, that'll be fun, because I'm ready to go from the experimental lab to make all this work in people, in patients. But I said, okay, I'll come, but only if you make a PET center for me, positron emission tomography. Why that? In my last year in Seattle, I realized that all the blood flow measurements I'd made in experimental models wouldn't work in people because it's just a different technology. And I had stumbled on a grant review session, and in the airport, a doc named Heinrich Schelbert, who had just built by hand the first PET scanner in Los Angeles. There had been one in St. Louis, but it wasn't very well developed. So they almost finished this machine. I met him. I said, look, why don't I take my experimental models down to your shop, and we take the images of the stenosis, the blood flow. And we did. It took a while, 2 weeks of work. And that paper won the Von Hevesy Prize for research. So I had the prize, I had the knowledge, Houston was wide open, I was ready to move. So I came and President Bolger recruited me and said he would support this. And the first, he said, we'll help you raise the money, because we had to have a cyclotron. I had to have a big team to build the camera, the scanners. And so he said, okay, we'll help you. And the first person that he met was A.G. McNeice. And A.G. McNeice was president of the Anderson Foundation, understood what we're doing, and he got our first big grant. And so then the fundraising went, and we were able to raise the funds to build the cyclotron building. I hired physicists and engineers from St. Louis and LA, and we built by hand the first whole heart camera, because the first one in Los Angeles was just a narrow little camera that would take 1 or 2 slices, and we needed one to cover the whole heart, so you could take the heart out and look at it like this. So we built it, it worked, and then we started to develop it for clinically. So the breakthrough was in this town of the greatest bypass surgery in the world. We had the first opportunity to do really very deep cardiovascular science. Then the second thing that happened that made it stick was that my wife's from East Germany, so I met a German doc named Rintrop at a meeting. Rintrop had done 5 cases of acute heart attacks by putting in a wire and giving a little bit of clot-busting drug and opening that up. So nobody knew him except me, and he was kind of known weird. So I realized that this was a big deal. You could actually stop heart attacks. So I sent the chief of the cath lab over, and he got some of the medications that he uses, brought it back. And we had the first 24-hour cath lab for acute heart attacks to do clot busting in the whole country. So that was the second kind of major evolution. Technology for imaging, the acute intervention for MI, that put UT on the map in the midst of this enormous boom in bypass surgery. And so those 2 factors then were the basis for UT evolving now to become the dominant cardiovascular center. And what we started kind of took seed, and it's gone far in excess of what I had ever imagined. For me, it was just a lot of fun and very scientifically interesting. So that's why I came to follow this dream. And there are always ups and downs, because it was quite innovative. This was really kind of shaking the foundations of cardiology, bypass surgery, coronary angiograms, and kind of a crude imaging. But all of a sudden we were looking at blood flow and saying, well, does this surgery work? Can you do it with lifestyle reversal? And so these are what put UT cardiology on the map. And we still are ahead of everybody else in the world. But most of that then kind of grew itself. And I've kind of gone along with it, focusing more on initially the lifestyle control and now the imaging. So the question is why I came to Tracker Dream. And UT at the time was very, and it still is. I went to lots of places. I went to Chicago, I went to Iowa. I looked at a lot of places for jobs. This is the only one that was really open, like kind of a frontier town where if you're lucky, work hard, get to know the people, get a right idea, you can go and nobody will stop you. They'll support you, you'll go. You can't make too many mistakes. In the wild frontier, you only get 1 or 2 shots, and then you're down. But it did work. And so then why did I stay? It's because it did work. And from this basic idea of physiology, what came out of it is what we call modern coronary physiology. What's that mean? The equations that I developed are the basis of what's called fractional flow reserve, where the guys in the cath lab measure the pressure in the coronary arteries and it gives additional physiologic information in addition to angiogram. Well, that came out of my lab. Coronary flow reserve is now being measured all over the world with PET. And so it's worked, it's expanded, it's put UT on the map, and it's allowed me to kind of blossom into the scientific world. And like all advances, I'm always interested in what works and what doesn't work. And over the years, if one learns that one has to let the data tell us what nature's having. Nature wants to talk to us about the heart. So nature's language is not always very clear. So you get data. And the data is a language where you have to figure out the clues. So if one has a preoccupation or a bias, you misread the data, and nature keeps its secrets. So what I've learned is that whatever notion I had that might be true, I have to test it. And if it doesn't test out, I got to throw it out, start all over. And this kind of a ruthless pursuit of the truth has now led to the modern era that we're in now, where everything that I did was true. But nature is more complex than any man's simple mind. And so the concept of FFR and coronary flow reserve and coronary blood flow alone, nature has very complex interactions. And it turns out that the next step is to understand those limitations. And that's why I'm here now. It's relevant to the COVID for two reasons. One is COVID can affect the heart quite profoundly, and it can affect the vascular system in the coronary arteries. It can affect the vascular system. In fact, it's a vascular disease. Vascular in the brain, the heart, and the kidneys. And it can affect the heart muscle itself, just like the brain cells themselves. And so the technology can also look at the effects of COVID. MRI is also important for that. And some people get the heart version of it, some people get the brain version, most people get the lung version. But it's useful for that. But even more broadly, when the hospital had to shut down the cath labs, there are a lot of people that weren't able to get angiograms and whatever they needed. So the teams realized that the PET scan can give them answers almost better than an angiogram. Now you need an angiogram to know where to sew and put a stent, but in order to know whether you need the stent in the first place, the PET scan is extremely accurate. And so they realized that since we could stay open, we're protected, we wear masks, we got a double door, we were able to provide a service that substituted for the cath labs. So the teams were starting to send us stuff. And now they realize that works so well that they're continuing that whole process. And so it's evolving to a very modern kind of step toward the management of coronary artery disease that's still very actively underway. Surviving in academia, so to speak. Proud of having planted the seeds of cardiovascular science in the world's greatest bypass center at the time, a seed that grew. And that's why we're here now. So that was unexpected. That was kind of a little bit wild in terms of the fundraising, the planning, the complex building, and then we had the cyclotron building, and as we were building a cyclotron, we had the opportunity to test a different source of radio tracers in a little box like this called a generator. And that worked extremely well. It's commercially produced. Then we had the cyclotron finally finished that was supposed to take the place of this. That was kind of tandem. So then we used the cyclotron for a while, but then in the flood of 2000, the whole cyclotron was destroyed. But we had developed this little box that we immediately were able to switch. So the cyclotron building was, in a sense, the scientific basis, because when we built it, there was no little box, there was no other way to do PET scanning. And it was the basis for all the scientific data that then led to this whole evolution. And the flood destroyed it, but we had developed the additional technology to go on without the cyclotron. And so these ups and downs of the environment in terms of the weather, there was a fair amount of politics, because whenever you do something innovative, there's always a group that's progressive, and there's always a group that's a little bit reluctant. And I had to learn to deal with that, and it worked. And I think the overall message was that this is probably a unique center in the world in which this kind of evolution can happen. I mean, if you think of Harvard and Hopkins, even the University of Washington, Yale, you think of any of those places, this couldn't have happened there. It didn't happen there, and they're still far behind. That's the unique place about that. It's the open-mindedness and the financial willingness to support good science, good arts. I mean, one of my patients did all the construction for the whole opera house on private. I mean, that's what Houston's about. And I think that's the magical part of Houston that makes it really unusual, and why this medical school is so unique of all the great medical schools in the country. Well, it's worked both ways. I've been through kind of what came from coming to the medical school, but that's really two ways. It helped the medical school become an international science center for arts and now for everything else. And it certainly, by doing that, allowed me to pursue this kind of dream and the scientific rigor that I wouldn't have been able to do anywhere else. So it's truly a symbiosis where we've affected each other that couldn't be done anywhere else. And it's had spillover in strange ways. The flood destroyed the cyclotron. So FEMA said, okay, we're going to provide X millions for replacement. And we had the little box that I didn't need a cyclotron anymore. So I said, okay, why don't we just develop a better scanner? And UT decided at the time, well, why don't we take part of that FEMA money, and why don't we develop a 3 Tesla brain MRI, and then you develop the heart PET. That's what they did. So that's why we have one of the world's most advanced 3D Tesla brain imaging that did all this, that's done just remarkable brain studies and continues to do so under Netanyahu. So even the innovation that started with the heart and bad weather spilled over into the same kind of innovation in other areas. And then the transplant team started to evolve, HVI started to grow, and all of this was kind of this mutual between just UT and this one wild scientist from Seattle coming down here to Texas, and that's a big change. Living in Seattle is very different than living in Texas. On the other hand, much better, because what I wanted to do could never been done anywhere else. So we've influenced each other, and that is reflected in influence in the whole world, which is a big surprise, but it's fun. I came here, and I walked on the campus, and the Weber Plaza was a solid mud field. There was no sidewalk, and I got my shoes all dirty. I had to go around. Of course, they would take care of me, but the place was a mess. And I walked into Herman in the ER. They had a defibrillator. Now this is a long time ago, this is not new. They had a defibrillator sitting there and it didn't work. And I went to the cath labs and turned on the eye machine, because I'd done a lot of cath work before then in Seattle. And looked at the patient, and you could barely see the heart because the eye tubes were so fogged up. And then I looked across the street, and I saw these towers that Denton Cooley and Mike DeBakey built. And I said, well, I got the stuff I got to do here. So that was the first impression, a mud field and a mess. But this openness to changing it. So I go from the mud field to here. So that's my impression.